On June 8, 2026, the strongest earthquake to hit the Philippines in 50 years tore through the seafloor off Mindanao. The magnitude 7.8 earthquake lifted sections of coastline, triggered a tsunami, damaged tens of thousands of homes, and sent thousands of aftershocks through the region. But the number that matters most isn't 7.8. It's what happened to the stress around the fault after the earthquake stopped. Because when scientists calculated how the rupture changed the surrounding crust, one nearby section of the tectonic system suddenly stood out, a section that has been quiet for decades. And now researchers are watching it much more closely. To understand why, we have to go back to the morning of June 8th. At 7:37 a.m., Philippine Standard Time, the ground began moving roughly 24 kilometers southwest of Cabalan in Sarangani province. The earthquake started about 55 kilometers beneath the surface and lasted around 70 seconds. The Philippine Institute of Volcanology and Seismology initially estimated it at magnitude 7.0, but as more data arrived, the estimate was revised upward. The final magnitude was 7.8. This was a powerful earthquake associated with the Cotabato Trench, a major subduction zone where one tectonic plate is being forced beneath another, and the effects were felt across southern Mindanao and far beyond the immediate epicenter. Roughly 1.5 million people experienced strong shaking, while more than 6 million people felt the earthquake in some form. In General Santos City, buildings were damaged and some structures collapsed. In Davao City, a condominium tower swayed dramatically during the shaking. A university structure was damaged, and across several communities, people rushed outside as the ground continued moving beneath them. The timing made the event even more disturbing. The earthquake struck on the first day of the new school year, when students and teachers were gathering for classes and ceremonies. In some communities, the first morning of the school year quickly turned into an emergency evacuation. But the earthquake didn't only move buildings, it changed the land itself. Along parts of the coast, the earthquake lifted sections of shoreline. Areas that had been underwater were suddenly exposed. The ocean responded almost immediately. A tsunami warning was issued, and PHIVOLCS recorded tsunami effects, including waves of roughly half a meter in Davao City, while larger measurements were reported elsewhere. Boats were pushed onto land, and coastal communities had to deal with a second threat after the shaking had already stopped. By late June, government reports had recorded 81 deaths, more than 300 injuries, and tens of thousands of damaged homes, although those figures remained subject to verification and change. This was not a small earthquake, but the physical destruction is only the first half of the story. The second half begins after the earthquake stops, because a fault doesn't simply go from stressed to unstressed when it ruptures. A large earthquake changes the stress field around it. Some neighboring areas can become less stressed, others can become more stressed, and the amount and direction of that change depend on the shape of the rupture and the geometry of the surrounding faults. This is where Coulomb's stress transfer modeling comes in. The name sounds complicated, but the basic idea is surprisingly simple. Imagine several locked doors connected to the same warped frame. You force one door open, the frame shifts. Some of the other doors might become harder to open, others might become easier. A major earthquake does something similar to the surrounding crust. It changes the mechanical conditions. Scientists can calculate those changes. And that's exactly what researchers Ross Stein and Shinji Toda did after the June 8th earthquake. They used a Coulomb stress model to examine how the magnitude 7.8 rupture changed stress on surrounding faults. One result stood out. A section of the Cotabato Trench northwest of the main rupture appeared to have moved into what the researchers describe as a stress trigger zone. The section is roughly 100 kilometers long and sits adjacent to the area that ruptured in 2026. And it is interesting for a very specific reason. It hasn't experienced a major earthquake for roughly 75 years. That alone doesn't prove the section is dangerous. A quiet fault can be quiet for many reasons, but researchers estimate that plate convergence has continued loading this part of the trench. Their calculations suggest that roughly 2 meters of slip has accumulated across the unruptured gap. Using empirical scaling relationships and the size of the fault area, they estimate that the section could eventually produce an earthquake around magnitude 7.6 to 7.8. That number sounds alarming. But the important word is eventually. The researchers are not predicting tomorrow. They're not predicting next month. They're not giving a date this year. They are describing a section of the fault that appears to have become more favorable for a future rupture. And there is another detail that makes the situation even more interesting. The loaded section hasn't behaved exactly as researchers expected. After a major earthquake, scientists closely watch the aftershocks. Their locations and patterns can provide clues about how the surrounding fault system has responded. But the section that the model calculates as having been pushed closer to failure has not yet produced the expected aftershock activity. Stein and Toda describe this as an important unresolved question. In other words, the model says the section has become more highly stressed, but the Earth hasn't yet given researchers the response they expected. That doesn't make the model useless. It makes the observation more important, because now scientists have something they can continue watching. And this is where another earthquake, thousands of kilometers away, becomes relevant. March 28th, 2025. Myanmar. A magnitude 7.7 earthquake struck near Mandalay along the Sagaing Fault. The Sagaing Fault is a huge strike-slip system running through Myanmar. Before that earthquake happened, researchers had already used Coulomb stress modeling to identify the Mandalay segment as a potential future rupture zone because of its relative quietness. The earthquake eventually happened there. The researchers had not predicted the exact day. They had identified a section that was mechanically concerning. Then reality eventually caught up with the model. That doesn't turn stress modeling into earthquake fortune-telling, but it does provide something scientists desperately need: a way to test a mechanical hypothesis against what the Earth actually does. And that same approach has now been applied to the Philippine Fault. In 2025, a team led by geologist Mario Aurelio at the University of the Philippines examined the Philippine Fault using historical earthquake data and Coulomb stress transfer modeling. They analyzed 64 earthquakes of magnitude, 5 or greater from 1973 through 2023. But instead of simply asking where earthquakes had happened, they asked a different question: which sections of the fault had remained unusually quiet? That sounds backwards. Why would a quiet section be worrying? Because quiet can mean two completely different things. It can mean a fault is creeping. The rocks are slowly sliding. Strain is being released gradually. Nothing dramatic happens. But quiet can also mean a fault is locked. The surrounding tectonic plates continue moving, but the locked section doesn't move with them. So the strain accumulates. From the surface, everything can look normal. Underground, the mechanical conditions can be changing year after year. Aurelio's team identified several sections of the Philippine Fault that had gone decades without major earthquakes. 3 were particularly notable: the Infanta segment in northern Luzon, the southern Leyte segment in the central Philippines, and the San Francisco segment in Agusan del Norte. The Infanta segment gets the most attention because it lies roughly 60 kilometers from Metro Manila, but that does not mean Metro Manila is about to be hit. The study does not say the June 2026 earthquake triggered the West Valley Fault. It does not provide a countdown to a Manila earthquake. The concern about Infanta comes from a separate analysis of how previous earthquakes change stress around the Philippine Fault. Aurelio's team found modeled stress increases associated with major earthquakes, including the magnitude 7.5 Regay Gulf earthquake of 1973 and the magnitude 7.7 North Luzon earthquake of 1990. The 1990 earthquake killed more than 1,700 people and produced a surface rupture roughly 125 kilometers long. Researchers also identified later earthquakes that occurred within areas where the model had associated previous earthquakes with increased stress. The 2022 Abra earthquake is one example. That doesn't prove every later earthquake was directly caused by every earlier one, but it gives researchers something extremely valuable: a way to test the model against real earthquakes. A model makes a mechanical hypothesis. An earthquake happens. Researchers compare the two. Then they improve the model. Then another earthquake happens. The process continues. That is how earthquake science becomes better at identifying risk. But there is one thing these models cannot remove: uncertainty. Because a fault is not a uniform object. One section can be locked, another can be creeping, another can have ruptured recently, and another can be receiving stress from an earthquake hundreds of kilometers away. Even two neighboring sections of the same fault can behave very differently. That's why a seismic hazard map isn't a crystal ball. It's a map of possibilities. And the June 8th earthquake gave scientists an unusually valuable opportunity to improve that map. A real magnitude, 7.8 earthquake happened. Researchers could measure its rupture. They could track the aftershocks. They could calculate how the stress field changed. They could compare those observations with existing models. That is a natural experiment. And natural experiments are rare in earthquake science because the planet doesn't ask permission before it runs one. It simply moves. Then scientists have to reconstruct what happened. The June earthquake also has to be understood within the longer history of the region. The Philippines sits inside an exceptionally complicated tectonic environment. Subduction zones surround the archipelago, while major strike-slip faults cut across it. The Philippine Fault itself stretches for roughly 1,500 kilometers through the islands. It isn't one simple crack. It is a network of structures responding to forces from multiple directions, and the region has experienced powerful earthquakes before. In 1976, the Moro Gulf earthquake struck southern Mindanao. It generated a devastating tsunami and remains one of the deadliest earthquakes in Philippine history. The 2026 earthquake was smaller, but it occurred inside the same broader tectonic environment. And the decades between major events do not mean the system has gone quiet. The plates are still moving. Faults are still accumulating strain. Some sections are creeping, others remain locked, and eventually some will rupture. The scientific question is not whether earthquakes will happen in the Philippines. They will. The important questions are more specific. Where is strain accumulating? Which sections are locked? Which are creeping? Which faults have recently been loaded by nearby earthquakes? And which of those signals actually matter? That is why the newly modeled section of the Cotabato Trench matters. It is also why the Infanta, Southern Leyte, and San Francisco segments deserve continued scientific attention. But they should not be turned into a list of the next earthquakes. They are areas where researchers have identified reasons to pay closer attention. That is a much more useful way to understand the science. Because whenever a major earthquake happens, people immediately ask the same question: what's next? And the internet often answers with a map, a red circle, and a terrifying prediction. Real earthquake science is much less certain. Scientists don't know exactly where the next major earthquake will happen. They don't know when it will happen. And they cannot turn a Coulomb stress map into a countdown clock. What they can do is measure. They can model. They can compare. They can identify sections that have accumulated stress. They can watch how aftershocks evolve. And they can learn from every earthquake that actually happens. That's why June 8th matters scientifically. Not because it proved that Manila is next. It didn't. Not because it proved another magnitude 7.8 earthquake is imminent. It didn't. It matters because a major earthquake changed the mechanical conditions around it, and researchers now have real measurements showing where that change may have occurred. The preliminary picture is unsettling. A neighboring section of the Cotabato Trench may have been pushed closer toward failure. The estimated slip deficit across that gap is on the order of 2 meters, and the researchers calculate that the unruptured section could eventually produce another large earthquake. But there is another piece of the picture that matters just as much. The section hasn't yet produced the aftershock response researchers expected. That uncertainty is important. It means the model should be watched, tested, and compared with what happens next, not turned into a prophecy. And that is the larger lesson here. The Philippine fault study identified quiet sections that had accumulated modeled stress over decades. The 2026 Cotabato analysis shows how a major earthquake can redistribute stress through the surrounding system. The Myanmar example shows how stress transfer modeling can sometimes identify segments that later rupture. None of those facts gives scientists a date, but together they show why researchers are becoming increasingly interested in something more realistic than earthquake prediction. They are trying to identify where the conditions for future earthquakes are becoming more favorable, and that has practical consequences. If you live in an earthquake-prone part of the Philippines, you don't need to know the exact date of the next earthquake to prepare for it. You need to know which active faults are near your home. You need to know whether your building can withstand strong shaking. You need to know where you will go if your normal route becomes blocked. And if you live near a coastline exposed to a major subduction earthquake, you need to know your tsunami evacuation route before the earthquake happens. Not the route you think you'll take, the route you've already identified. Ideally, the route you've walked. Keep water, keep essential medicine, keep lighting, keep communication equipment, keep important documents, somewhere they can survive water and debris. None of that predicts an earthquake. It simply reduces what the earthquake can take from you. Because scientists still cannot tell us exactly when the next major earthquake in the Philippines will occur. But they can tell us where stress is accumulating. They can calculate how one earthquake changes the surrounding fault system. They can compare those calculations with decades of earthquake history. And now, after the magnitude 7.8 earthquake of June 8th, they have another major event to study in real time. The earthquake lifted coastlines. It generated a tsunami. It damaged communities. It produced thousands of aftershocks. But scientifically, it also changed the stress map beneath the region. Some areas became less stressed. Others became more stressed. And at least one neighboring section now deserves closer attention. The Earth has already moved. The stress has shifted. The models have been updated. And now researchers are watching what happens next. Because the ground doesn't send a warning with a date and time. It leaves clues. And the better scientists become at reading those clues, the better chance we have of understanding where future earthquake risk is building before the ground moves again. If you want grounded, fact-first coverage of earthquakes, volcanoes, climate events, and the other forces changing our planet, subscribe to WideView. And tell me in the comments, do you think scientists will eventually be able to identify the world's highest risk fault zones before they rupture? Because the goal isn't to predict the exact moment the Earth will move. It's to understand the warning signs well enough that when it finally does, we're not seeing them for the first time.